You're going to do a little probability and statistics review today, and we're going to start off with probability. And we're going to look at simple probability first. And remember that simple probability is a ratio, and a ratio is a fraction. And the way that you set the fraction up, in the numerator, it's what you want to occur. And in the denominator, it's the total number of possibilities. And so the first thing that we should try to do is get the total possibilities and place that number in the denominator. And so in this example, it says Shira conducted an experiment with a spinner, and the results are shown in the table below. And we can see the different numbers on the spinner, 1, 2, 3, and 4, and how many times it landed on each of those numbers. And it says, based on the data, what is the probability of spinning a 3 or a 4 on the next spin? And so the first thing we're going to do is try to figure out, well, how many times did she spin the spinner originally? And so we're looking at the times landed. And if I add up all of these numbers here, that's going to be my total possibilities. That's going to be in my denominator. And so I count these up. 8 and 4 is 12, and 5 is 17, and 3 makes 20. And so I know that my probability is going to be something out of 20. And now I'm interested in trying to figure out how many times it landed on a 3 or a 4. And so I look here at these two values. That's the 3 and the 4. And it landed on the 3 5 times and the 4 3 times. 5 plus 3. That makes 8 out of 20. And so this would be our probability here, 8 out of 20. But you notice your choices here, well, none of them say 8 out of 20. And so what we're going to try to do is see if we can simplify this. And we can. Both the 8 and the 20 are divisible by 4. And so if we divide the 8 by 4, we get 2. And if we divide the 20 by 4, we end up with 5. And there we see choice C. There's our answer. The probability is going to be 8 out of 20, or equivalently 2 out of 5, that it's going to land on a 3 or a 4 on the next spin. And that's how we do our basic simple probabilities. Again, it's what you want in the numerator divided by, in the denominator, the total number of possibilities. And we're going to move on to compound probabilities now. There are two types of compound probabilities, and those are independent and dependent events. In independent events, it's when one game or one item does not affect the second. With dependent, though, it's when the second simple probability is affected by the first simple probability. We're going to start with independent events first. And this is when an item gets replaced. And so what we've got here, we've got a marble. We've got marbles in a jar. There are 3 green, 4 red, and 2 blue marbles. And we're going to pick a marble, and then we're going to replace it, and then we're going to pick a marble again. And in our first question, we want the probability of getting a red marble and then a blue marble the second time that we try. And so the first thing we should try to do is, again, come up with what our denominator is going to be, count up how many marbles are in the jar. We see 3 plus 4 plus 2. Well, that's going to give me 9 total marbles. And so I know for my first probability of picking a red marble, well, there were 4 of them. It's going to be a 4 out of 9 probability. Now remember, we replace that marble. We don't keep it out. We put it back in the jar. And so for my second probability, it's also going to be out of 9. And I'm looking for a blue marble this time. Well, 2 of the 9 are blue, and so that's going to be a 2 out of 9 probability. And then to get the compound probability, you take each simple probability and you multiply them together. And this is going to give us a probability of 8 out of 81 of getting a red marble and then a blue marble on the second try. In the next example, we want to get a red marble and then another red marble, keeping in mind we are replacing the first marble. Okay, well, from up above, we knew that getting a red marble on the first try would be 4 out of 9. And since we put the marble back in, there are still 9 marbles in the bag. And again, 4 of them are red. And so we have 4 out of 9 probability of getting a red marble the second time as well. And now when we multiply our simple probabilities here, 4 ninths times 4 ninths is going to give us 16 out of 81. 16 81st is the compound probability. Okay. Dependent, again, this is when the second simple probability is affected by the first simple probability. This is when an item is not replaced. And so we're going to pick a marble, but we're not going to put it back in the jar when we're done with it. We're going to keep it out, and then we're going to pick another marble. And it's the same that we had before, 3 green, 4 red, and 2 blue. So I know for my first marble, well, there's 9 in the bag, and again, 4 of them are red. So it's going to be a 4 out of 9 probability of getting a red marble, but I'm not putting that one marble back in that I just chose, and so now for my second choice, it's only going to be 8 marbles that are in the jar, so it's going to be out of 8. And since it was a red marble, well, the blues, there's still 2 of them in the jar. 2 out of 8 is going to be the probability of getting a blue marble on the second try. And now when we multiply 4 ninths by 2 eighths to get our compound probability, we end up with 8 out of 72. which can simplify down to 1/9. In the second example, again, while we're trying to get a red followed by another red, and again, there's 9 to start. 4 of them are red, so it's going to be a 4 out of 9 probability of getting a red the first time. But now we've just taken 1 red marble out of the bag. So again, there's 1 less marble, which means there's going to be 8. And that 1 marble we took was red, so there's no longer 4, but now there's only going to be 3 red marbles in the bag. So it's a 3 out of 8 probability of getting a red marble on the second try. And now when we multiply the simple probabilities together, 4/9 times 3/8, we end up with 12 out of 72. And that will simplify as well all the way down to 1/6. And that is going to be our compound probability this time. Okay, so those are the 2 types of compound probabilities. There's independent, when the second probability is not affected by the first probability, and there's dependent when the second probability is affected by the first simple probability. We're going to use our probabilities now to make predictions. And in our first example, we're told that Dan rolled a number cubed 20 times, and he rolled the number 3 6 out of those 20 times. Okay, and so we want to know what's the experimental probability that Dan will roll the number 3 the next time that he rolls the number cube. Okay, well, what we're going to do, we're going to take the probability that he landed on a 3 the first time, which was going to be a 6 out of 20 probability. And then we're going to look and see if that's one of our choices, and it's not. So we're going to see if we can simplify that, which we can. We can divide each of these by 2. And so we can see that it's going to be a 3 out of 10. There's a 3 out of 10 experimental probability that Dan will roll the number 3 the next time that he rolls the number cube. The follow-up to that, in part B, it says, which best describes what would likely happen if Dan rolled the number cube another 80 times? And so we're going to predict from what happened before. We knew that 6 out of the 20 times that he rolled it before he landed on the number 3. We're going to set that equal to a probability out of 80. Since we're going to roll the number cube another 80 times, how many times is he going to land on the number 3? Well, we're not sure, so we're going to use the variable x. And we're going to make our prediction by solving this proportion here. Well, I know to go from a 20 to an 80, I would have to multiply by 4. So I'll do the same thing in my numerator. I'm going to do 6 times 4. So I know that x equals 24, meaning that I could expect to land on the number 3 another 24 times out of the 80, which is going to be choice B. In question 2, a light bulb manufacturer found that out of 200 light bulbs, 15 of them were defective. Then how many light bulbs should the manufacturer expect to be defective out of 2,400 light bulbs? So again, we're going to use our experimental probability to make a prediction out of the total 2,400 light bulbs. Well, we knew that 15 out of the 200 were defective, and we're trying to figure out how many out of the total 2,400 were defective. And so there's the proportion that we can set up. 15 over 200 equals x out of 2,400. And again, I'm going to try to solve this proportion, and I can tell that if I go from a 200 to a 2,400, I would have to multiply by 12. And so I'll do the same thing in numerator up above, 15 times 12, and that's going to give me a value of 180. So choice D, out of the 2,400 total light bulbs, I would be able to expect 180 of them to be defective. In question 3, we're trying to figure out how many different meal combinations there are. Dan is going to Delmonico's restaurant. There are 7 different appetizers, 8 meat entrees, and 5 desserts on the menu. If a meal consists of an appetizer, an entree, and a dessert, how many different meal combinations does Dan have? And to be able to figure this out, we're going to use the counting principle, which means that we take our number of choices for each part of the dinner, and we multiply them together to get our total number of combinations. And so we have an appetizer, we have a meat entree, and we have a dessert to choose from. And we're told that there were 7 different appetizers, there were 8 different meat entrees, and there were 5 different desserts. And so to get the total amount of combinations, well, I'm going to multiply these values together, 7 times 8 times 5, and that's going to give me 280 meal combinations. 280 meal combinations exist at Delmonico's given these choices. In our next example, we're going to be making a tree diagram. A car can be purchased in blue, silver, red, or purple. It also comes as a convertible or a hardtop. We're going to make a tree diagram and list all the different styles in which the car can be purchased. And so the first thing that this person would have to do is choose their color. And so since there are 4 different colors, we're going to make 4 different branches to start our tree diagram, and the colors again were blue, silver, red, and purple. And then the next choice they have to make is, do they want to have a convertible or do they want to have a hardtop? Now, the color of car that they choose does not affect what kind of top that they can have. So off of each one of these colors, we're going to need 2 branches because there are 2 choices. It could either be a hardtop or a convertible. And so I'm going to list that all the way through for each color, either a hardtop or a convertible. And now I'm ready to list out all my total combinations. I could have a blue car with a hardtop, a blue car as a convertible, a silver car with a hardtop, a silver car with a convertible, a red with a hardtop, red car as a convertible, a purple car with a hardtop, or a purple car with convertible. I count all of those up, and there are 8 total outcomes or different ways that we could make our car. Now, part B says if green and black get added as color options, how many different styles exist? Now, I'm not going to make another tree, but I'm simply going to do the counting principle again. I have to choose my color, and then I have to choose what kind of a top I want. Well, when I add in green and black to what I had before, now there are 6 different colors. There are still 2 top choices that we can make. I multiply those together, and that's going to give me 12 different styles that exist under these conditions. We're going to move on to some statistics review now. We're going to start by looking at the measures of central tendency, mean, median, and mode, and we're also going to look at the range as well. In the first example, we're looking at daily low temperatures, and there's our list, and we have to find the mean, the median, the mode, and the range for those low temperatures. And we'll start off with the mean. Remember, the mean is the average, and so we're going to have to add all of these together. And when we do that, we end up with 17. And then we have to take that number and divide it by how many numbers were in the list, and there were 8. And so we're going to do 17 divided by 8, which is going to give us a mean or an average of 2 and 125 thousandths. Next, we're going to find the median. And in order to find the median, the first thing that we have to do is arrange our data from least to greatest. And so I'm going to go ahead and do that right now. And there's our list in order from least to greatest. And there are 8 pieces of data in the list, which is an even number, which means that 2 numbers are going to appear in the middle. And the 2 that appear in the middle are the 1 and the 2, and I have to average those now to figure out what the median is going to be. So I'm going to do 1 plus 2, and I'm going to divide that answer by 2. And that becomes 3 divided by 2, which is going to give us a median of 1 and 5/10. The mode, that's the number or numbers that appear most often in the list, and by looking here I can see there's 3 1s and there's also 3 2s, which appear more often than the 0 or the 8, and so the 1 and 2 are going to be the mode. You can have more than one mode in your list. In order to find the range now, we take the highest, which is 8, and we subtract off the lowest, which is 0, which is going to give us a range of 8. In part B, they want to know which measure of central tendency best represents the daily low temperature. Well, I would argue in this case that the temperature at 8 degrees is significantly higher than most of the data, and so I'm going to say that 8 is an outlier. When there's an outlier in your list, then you're going to have to use the median. The median is resistant to outliers when the mean is not. If there wasn't an outlier, we would choose the mean. If the data wasn't numerical, well, that's when we would choose the mode. But since there's an outlier here, we're going to have to choose the median. In example 3, we're trying to pick a sample. In this case, we want our sample to be representative of the entire student population. When choosing a sample, you always want your sample to be completely random, and every member of the population should have a chance to be included in that sample. And so looking at choice A, it says we're going to survey every 10th, 7th grader that enters the library. Since we're only looking at 7th graders in the library, that's not going to be the best choice because we're excluding all other grades and students not in the library. In choice B, it says surveying every 10th student who goes to the library. Well, again, this is better than choice A, but again, we're only looking at students in the library. We're excluding all other students that aren't in the library, and so that's not going to be the best choice either. In choice C, it says surveying every 10th student who enters the school. That one sounds pretty good. Let's just check choice D to be safe. It says surveying every 10th girl who enters the school. Well, here we're excluding all of the boys, and so that one's not going to be the most representative, and so it's going to have to be choice C. Okay, that's the one that's most representative of the population. It's random, it's every 10th student, and it includes every member of the population, every student that enters the school.